Alrighty. Well, welcome to another session. Um, let's just make sure we got everything going good here. I'm not muted. We've got people on. Got people online. Hopefully, you can hear me very well. And we're going to be leveraging the chat session. Today's topic is going to be on selective coordination and the overcurrent protected devices. So hopefully you're in the right session here. So let's do this. Just to get started, I want to go over some logistics and some basic information on what we're doing here with regard to registration. I know we've had some registration issues. I want to welcome everybody first. Welcome to this session. Very glad we're going to be testing the WebEx portal. We have over 400 people signed up. We had more than 300 people on our yesterday session. I've got 55 right now on YouTube. We are live streaming. I'm getting both of these things done. So, and it's just a one-man band here, so bear with me. Thanks for joining today's session on selective coordination. I had some registration issues. I know we had some people who said they didn't have the link. I'm working on a new method to get that done for next week's sessions. Those are going to be on NEC 2020 code changes. So you'll want to keep an eye out for the registration for those. I'll have 3 days of that: Monday, Tuesday, Wednesday, and Friday. Thursday, I believe I have a web presentation for a customer, but after that, I'm going to do some circuit breaker basics. I think I'm going to do that in the afternoon on Friday or Thursday. So stay tuned for that. Okay. Oh man. So let's. So PDH. So here's what we're going to do on PDH. Because so there are some people on YouTube on the live stream that would like to have the opportunity to get a certificate. How I'm going to do this is I'm going to have a sign in at the beginning. It's sort of like when you walk into a room and you register or you sign a sheet. I'm going to flash up a Mentimeter code that you can go online at menti.com, enter those digits. So you're going to want to get a little piece of paper to write that code down. I'm going to keep it up for as long as I can. I don't want to waste everybody's time with that, but I'm going to have that as your point of entry. That'll let me know that you were here at the beginning. And then at the end, I'll have another similar sign in or sign out type of deal with a short quiz. And then I'll marry those two up. If you were here in the beginning and you were here in the end, you took the quiz, I will give you credit for that, and I will send those certificates. Now, I'm not, I've had some questions about people asking about whether or not, are they certified in New Jersey? Is it okay for Texas? These are just, I have the documentation that you were in the class. I didn't reach out to any jurisdictions. It's not CEU credits. These are PDH, professional development hours. Many from an engineering perspective, a lot of people take these. The knowledge is worth probably more than the PDH credits. And please use the dialogue box to ask questions and things of that nature. But in any case, I will be live streaming this, and it will be posted afterwards. Now, yesterday's session is up there. And it was immediately posted afterwards. I'm going to have to edit this out because I am going to have to take out those Mentimeter codes at the beginning and end. I don't want someone to watch this online and then fill those things out and then think they're going to get some PDH credits. So I'm going to take those streaming out. So those are just some of the logistics. I want to make sure I have everything good there. So all right. So let's go to my on mute. We did pretty good yesterday. We only had one caller who, I disabled the videos so nobody can use their video cameras. That's probably a good thing for many different reasons. But please use the chat. I can see people using the chat. I can't answer the question on how to change your language back to English. But anyway, it goes to presenter screen. Can we just shut that screen down? After your code Menti, it goes to presenter screen. Hold on, I'm going to check the Mentimeter link. So give me a short second. I'm going to make sure that I have that on. Automatically putting your information is, but after you're done, if you are able to enter your information on Mentimeter, then you get to the end, you can just close that screen. I'm just going to check to make sure that we're getting. Class survey 2023, this is the 31st, class attendance. let's just take a quick look and make sure that we are getting people to enter their information. And it's not self-driven. Let me open that. I believe all of that should probably be looking good. So make sure you just put your information in there, and if you've entered your data, you can close that. You won't need it until the end, and you'll bring it up again for the last portion of it. Okay, so yeah, so I'm getting. It looks like, okay, so I'm getting a lot of registrations in there, so the numbers are going, so that means that form is working. You can just close that down when you're done. All right, good questions. Oops. Okay, so let's get back to the live stream. We've got 79 people on board. And let's move on to the next slide here. So, Chad, I think if you were here yesterday, if you're familiar with WebEx, there is a little chat screen up in the top right-hand side of your screen. You should be able to see, move your mouse around, find that. Once you find it, if you click it, you'll bring up a little dialog box like you see here that has the chat session, and then make sure that you can either, obviously where it says to everyone, you can chat individually amongst each other. You can send a private message to me, and you can also chat to everybody. This is, what I like to do is foster communication amongst people. Now, we can't all talk. We can't all talk at the same time, obviously, but we can talk via the chat. Please enter information. If you hear me misspeak, if you hear me, if you want to contribute some of your knowledge to the information, use the chat session for that. I really would appreciate it. I think everybody would appreciate that. So we got David Castro we got Costa Rica. So there should be nothing on that on the Mentimeter thing. Just entering your information.
What I like to do is foster communication amongst people.
Okay, somebody, it's just, I got some echo.
We can't all talk.
Somebody's talking.
We can talk via the chat.
We got to figure this one out.
If you hear me to speak,
please mute your phones.
If you want to contribute some of
there it
your
is.
Information, use the chat session for that. I really would appreciate it.
There you go. Found you. Now, Mr. Platt, you're the culprit, buddy. I'm calling you out. All right, so let's move this ball forward. Going down the line, I'm going to periodically try to look at this chat session. So here's the thing. Every time I look down at that chat window, I get discombobulated. So I'm going to try not to look in there. But in any case, I will try to do that, and I will try to answer the questions. I'm going to provide this information at the bottom of the YouTube channel link, and I will probably send this out when I send all the certification. But these are just links that were in the meeting invite. Many of you may not have had the meeting invite, but there are some really good references I will share with everybody as we, that you can download at a later date. So I will send that out to everybody. All right, so I did send a quiz out to a lot of individuals, most everybody. I had a really good showing on the quiz, but before I get to the quiz, and because most of this presentation is going to be driven off that quiz, because you're going to have a lot of fun when you see some of the results. But I'm going to focus right now on on some pre-information before we get to the quiz. So I'm going to focus on some of the basics around selective coordination. That'll help us understand some of the right or wrong answers as we move through that quiz. So the first thing we have to understand when it comes to selective coordination are the time current characteristic trip curves. For many people, it may be the first time you've ever seen a time current characteristic curve. It may or may not be the first time, but I at least want to go through the logistics of what a TCC curve is. You have a horizontal axis and a vertical axis, obviously like any graph paper. The horizontal axis gives us the current values, and the vertical axis is time. So current across the bottom, and you'll notice that the distance in between each of these gradients they get smaller as they go. So from 10 to 100, they're not evenly separated from each other. That's called logarithmic scale. And we do that because if we were actually plotting individual equally distanced lines, this graph paper would be a mile long. So we try to bring it all in closer to each other so I can get to 10 to 100,000 on this curve, on this graph paper, and show a curve that is all on one screen and it means something more. So in any case, you'll always want to reference as well. Here's an important part of the pie here is down here on the bottom where it says current and voltage, reference voltage. These are, you always have to look at the bottom of any time current characteristic curve to put this into perspective. Sometimes it'll be current in amps times 10 or times 100. That means anything across there. If it was times 10, you take 100. Where it says 100, it's actually 1,000. If it was times 100, it would be 10,000. So you have to just do the math and look at the reference down at the bottom of the TCC curve. Very important area. And again, that is all current. Across up the vertical axis is time. So these are time in seconds. You notice we go from 0.01 seconds to 1,000. You'll hear 0.01 seconds a lot when people talk about selective coordination. It just, for me, it just grinds on me like your nails on a chalkboard. I'm not a big fan of talking about selective coordination with regard to time because as you'll see as we go through this, it's about a little bit more than that. But in any case, it starts at 0.01 seconds. All your graph paper starts there. Pretty much all of your software applications are going to be using a 0.01 as that bottom unit. And most of your time current characteristic curves that you get from manufacturers will start at in that area. We're going to talk more about that as we move forward as well. So this curve here is one. This is showing you a time current characteristic curve for a molded case circuit breaker. It could be an insulated case circuit breaker, and we'll get into those differences as we move forward. But you'll notice across the bottom is current, and up the side is time. So what's nice about the time current characteristic curve, what I always liken it to from a circuit breaker perspective or a fuse, it's like the resume of that device. It will tell you how it will perform based upon how much current you pass through it. So in this case, we have a circuit breaker that I know that if I put 20,000 amps through this breaker from the line lugs to the load lugs and I pass it through that breaker, it's going to take anywhere at a maximum clearing time of 0.16 seconds and a minimum clearing time. You'd have to look at that those gradients. You have 0.01, 0.02, 3, 4, 5, 6, 0.065 seconds. So the band is an error margin, and the band is there for a lot of different reasons. You know, these devices don't instantly operate. They have to do some thought process. They have to think about what they're seeing. They have to tell the device to open. The contacts have to separate, and there is some margin that you have to take into consideration for all that. So it can trip anywhere. The left-hand leading edge of this curve tells you that overcurrent protective device will trip no sooner than that. And then the lagging end, the far end, to the right side of that curve, it tells you that that's the maximum clearing time. So you'll see the trip curves will be a little differently. You can always spot an electronically tripped unit because they have very nice straight lines like this. A standard thermomagnetic circuit breaker, I call it the beer gut. It'll have a nice big fat band up there in the overload region. The instantaneous is a little bit fatter as well. But in any case, the TCC curve gives you current and time, and I can tell how long it takes for this breaker to trip when I pass any amount of current through it, as long as I can plot it on this screen. Okay, so that is what we call the time current characteristic curve. And so that should give you an understanding as we walk through this presentation. We're going to be showing those curves. So now I want to get into the topic of selective coordination and just the basics and understand what is selective coordination. Now, we understand that we have an overcurrent protective devices. We don't just have overcurrent protective devices sitting by themselves. They work as part of a system. And the selective coordination has been around, and this topic has been around. I've got the Donald Beeman Industrial Power System Handbook that goes back to the 20s. They talk selective coordination there. As long as we've had overcurrent devices, we've had this terminology of selective coordination. Selective coordination is the process of helping us understand how devices work and interact with each other. So, for example, if I have a fault on my system, the way I would want this to work, I would want the overcurrent device closest to the fault to clear it and not take out any other portion of my power distribution system. So, for example, in this case here, I have a fault downstream of a feeder. The feeder breaker opens and clears the fault. I don't have any other overcurrent devices clearing. This is like a good example. You're in the house and it's Super Bowl Sunday. Steelers are playing on TV. They're winning as usual. And you're sitting there watching the game, and you've got people in the other room. You've got people upstairs using hair dryers. They're all getting ready because they're going out to the Super Bowl party afterwards because, they know the Steelers are going to win. So at the end of the game, they all want to go to a party, and all of a sudden there's a critical moment of the game, and you're watching it, and someone turns on too many hair dryers upstairs, and instead of taking the branch circuit that feeds the bathroom or wherever they're located, they take the main out to the house. That would be ungood. Now everybody's out of power. You missed the game and you're really upset. So that's what you don't want to happen. What you want to happen is you want just that portion of the circuit that is having issues to be isolated from everything else, and only that portion of the system. You have to understand that basic fundamentals, that's your end goal. Your end goal is if I have a fault on a system, the closest overcurrent device trips. If I have what we call a cascading event, I could have both of these breakers or fuses open, or I could even have the upstream open and the downstream stay closed. So I could have both open, or I can have one missile. I could go all the way up to the main. I mean, we've all heard those stories where they have a fault downstream in the plant and they took the main out because of ground fault protection of equipment on the service entrance equipment. So, but in any case, it's really important to understand that is your end goal. You want to isolate the fault closest. You want to isolate it by opening the breaker or fuse closest to the fault. Now, we can look in Article 100 of the National Electrical Code where they have a definition. The definition basically tells you exactly what I told you, but it brings in a couple more parameters. Selective coordination per Article 100 tells us that we need to localization of overcurrent conditions restricting outages to the circuit. So you want to restrict outages. You don't want to take the whole house down. You just want to take the bathroom down where all of those hair dryers are being plugged in. You want to accomplish it by selecting the right overcurrent protective devices. So you're picking devices based upon time current characteristic curves or other information, which I'm going to get into. There's a lot more tools to the selective coordination engineer than what there used to be. And you want to protect for all fault currents from the overload to the maximum available fault current. So we're considering all currents that pass through any series of devices. And that's a very important aspect. I mean, there are a lot of debates in the industry about, do we selectively coordinate to the three-phase bolted fault? Do I selectively coordinate to some other fault current, or do I just ignore fault current? We're going to talk about those discussion points, and those are all valid discussion points depending upon whether it's a code requirement or it's a design goal of yours. There will be reasons to do both of those. But we're going to talk about those as we move forward. But that's basically selective coordination. Is you are looking at the performance of your system based upon current passing through the overcurrent protective devices. Now, when you think about reference materials, IEEE documents and IEEE standards echo this definition, and our goals in selective coordination. This is taken from the healthcare facilities book. I call it the White Book, IEEE Standard 602, page 113 of the 2007 edition of that. But it tells you the selectivity and maximum safety personnel or critical engineers should always perform total short circuit coordination and component protection study. And again, equipment protection. We talked a little bit about equipment protection in our session yesterday. And I don't know if we're going to have enough time today, but there's a level of, you're going to have to review the equipment protection based upon the settings of your overcurrent devices to achieve selective coordination. And hopefully we'll touch on that today. Generally, coordination is demonstrated by plotting the time current characteristic curves and comparing that with the fault current. So what I'm showing here are 3 overcurrent protect breakers, 1, 2, and 3, and they're in series with each other. And we would typically plot those time current characteristic curves, overlay those with each other so I can see what is closest to my load, what's the next upstream, and what's the next upstream. How many devices you put on a TCC curve will vary. I know when I used to do this, I got a passion for this because I did this when I worked for Gilbert Commonwealth and did a lot of this, a lot of studies. And I would sometimes put 3 overcurrent devices on the curve, or I would put 2, depending upon the system. But you're basically comparing these overcurrent devices, and you're comparing them with with either the equipment that you're trying to protect or other overcurrent protected devices that are upstream or downstream. So this is an example of one that shows the transformer damage curve. So another thing that you will see on a time current characteristic curve is not just the circuit breakers, but you will see lines associated with motors for motor starting, which I have some images of those as we move through this presentation. We will show the damage curves for other equipment that we're trying to protect. Transformers are one of those. So these curves that you see, let's see if I can do this without killing myself here. These curves here that you see are the transformer damage curves. What's not shown here is sometimes we will, or most often we'll put the damage curves for conductors, and what those look like are basically a straight line like this. Just basically, and that's a terrible straight line. That's like 4 or 5 straight lines. But in any case, you'll see a line somewhere on here that represents the damage of those equipment. So what those damage curves show you is that just like the overcurrent device time current characteristic curve for the tripping, the damage curves shows you when you're going to have a problem with putting too much current for too much of a longer period of time. So we want to make sure that we protect equipment. We want to make sure that downstream motors start and we don't trip on inrush. We want to make sure that the transformer energizes without tripping the overcurrent device. And this tool, the selective coordination, the time current characteristic curves, is the tool that helps us get all of that done. I see a question. Are conductor damage curves insulation damage, termination damage, some combination? They are insulation damage. So what we use are the ICEA equations to establish that. It doesn't give you the termination. You always have to follow the National Electrical Code to make sure you're applying the conductor correctly. That damage curve is the thermal capabilities of the insulation on those conductors, and that's the limiting part, right? If you think about a conductor, I have the annealing damage for the conductor itself, where it becomes it deforms and whatnot. I may have loose terminations. I have the portion from a current perspective that it'll just vaporize, but in reality, the trip curve, the damage curve for the thermal damage curve is basically the insulation, because that's the weakest link. So let's talk. I see. Can you explain the multipliers at the bottom of the curve? So those are based on, remember, I'm plotting all of these at different voltages. So if you have to do the voltage ratio on whether it's on one side or the other side of the transformer, or depending upon what voltage level you want to reflect these to. That's probably a little bit more detail than we can go into at this point. But but suffice it to say, all of these breakers may not be at the same voltage level. Some may be on the primary of that transformer at a different voltage level. So there may be two different transformers in the picture as well. So there may be two different levels of voltage, and we have to put those all together so we will reflect these curves from one side of the transformer to the other. And that is a part of one of the questions that we had in the quiz, which we're going to talk about the impact of a transformer on the time current characteristic curves. Okay. I see, I'm just going to check on a thing. I got 100 people on YouTube streaming. My stream health looks good. Everybody looks good. I see people using the chat box, so thank you very much. So selective coordination can be a requirement per the National Electrical Code, or it can be a design goal. We'll talk about available fault current. You use the maximum available fault current. It might be the three-phase, or it could be the phase to ground fault. That's what you'll be plotting. We'll talk a little bit more about that as we move forward. These are the sections in the National Electrical Code that have a requirement around selective coordination. If you'll notice that the whole concept entered the code in 1975 around ground fault in healthcare facilities, and they have to selectively coordinate the ground fault devices for all currents, all times, as it says in the National Electrical Code for ground fault. The definition didn't enter into the NEC until the 2005 version of the NEC, but we had selective coordination in 1993 around elevators, and then it sort of blossomed after 2005, and a lot of that was driven by just the technical awareness of what was going on. We had various industry people recognizing that that reliable power distribution systems is important to life safety critical systems. So if you look, fire pumps, emergency systems, legally required standby systems, elevators, these are all life safety areas in the National Electrical Code, and they all have requirements around selective coordination. Healthcare is a little bit different. They just do coordination, and if we have some time, I'll go over that as well. Now, customer needs usually drive reliable power system design. And in addition to selective coordination as a requirement in the code, there are a lot of industrials that will use this to help ensure reliable power distribution systems. You'll see a lot of your petrochem facilities, your automotive facilities will drive for a selectively coordinated system. Remember, if you think about a design goal, I'm either an egress-driven design or a shelter-in-place design. An egress-driven design, you know, if it's a commercial building and I can get people out of a building within so many minutes, I'm not necessarily going to see a generator on that facility because I'll have battery backed up lighting and things of that nature. Tall buildings will always have a generator because you'll have to operate and make sure you have enough time to get people out of the building and you keep the power on. You'll have elevators that will require some backup generation. And the shelter-in-place perspective, you know, your healthcare industry, and I would say, you know, in some cases, I may have a factory floor and I want to keep it running. I don't want to have all my people go home from work because somebody hit a pole outside or because, you know, someone made a mistake at a neighboring facility and now my whole neighborhood is out. You know, I will have that. I want to keep my plant running, and that could be a financial reason to do that and not just a life safety. And I use this as an example. Unplanned outages in the refining and petrochem can cost millions of dollars in lost production. So you think these individuals are concerned about coordination. They don't want half of their plant to go out because somebody took a forklift and rammed it into a piece of conduit, right? They lose upwards of $704,000 per hour. And I'm sure there are probably some people on the phone or on this this call that will say that that's an old number. I mean, this is an older number. It's one I've used and I continue to use just as an example. Now, the other automotive facilities, $22,000 a minute based on a survey done in 2005. And that's a lot of money a minute. So you're going to want to worry about reliability with regard to the power distribution system. So it's about keeping the facility running when things go wrong in the system. So now what I want to do is I'm going to bring up the quiz results because that is what's going to drive this program. And I think everybody who took the quiz, for doing that, I'm going to first bring up the first quiz question. Quiz question number 1. I use this a lot whenever I do work with consultants. I'll have a lot of people say, "Well, listen, we understand selective coordination. I don't need you to talk about the basics. Just tell me how you can make my life easier." And I do that only on one condition: if they pass this quiz. So, do these two circuit breakers selectively coordinate? Let's take a look at what we had from an answer perspective. Had 123 people responding. 79 say yes, 8 say no, 25 say maybe, and 11 say they don't know. Okay, the 25 that say maybe, you should be standing up right now behind your desk, giving it the high five, jumping around, because you got that one. You got that one right. And let's take a look at why. The 81 that said yes, I know why you said that, and hopefully after this we're gonna take away something, and you're gonna maybe hopefully learn a little bit about those curves and this topic. So let's walk through this discussion. And I like those results because it always amazes me. But this is one of the most fundamental things that people miss when they look at trip curves. So if I assume that both of those circuit breakers are going to see 500 amps, so let's say that my fault, this panel board is at the end of a long run, and it sees a fault downstream of that BAB20 circuit breaker of 500 amps. I know from reading this trip curve that the downstream BAB20 is going to trip instantaneously, because the curve, it hits the 0.01 seconds, which means I'm going to trip probably faster than 0.01 seconds on that breaker. But the blue breaker, the F-150, the breaker, not the truck, that's going to take upwards of anywhere between 10 to 43 seconds to trip. So if my fault current is 500 amps, I can say, yes, I selectively coordinate. If I don't plot fault current, which I didn't in that quiz question, you don't have enough information to tell me whether or not it selectively coordinates, because you don't know how much current is going to pass through it. For 500 amp fault downstream, yes, it will trip, and it will selectively coordinate. Now, if my fault current is 1,000 amps, so if my fault current is 1,000 amps, now I'm into the instantaneous region of both of these circuit breakers. Based on what I'm seeing, I don't know if I'm going to coordinate or not. My best guess would be that it doesn't, based on what I'm seeing here, because I am now into the instantaneous region. That the F-150 can trip anywhere from 0.01 seconds all the ways up to about 11 seconds, or maybe a little bit, maybe around 11 seconds. It could trip, I call that no man's land. It could trip any time in there. I don't know for certain when that F-150 is going to open on 1,000 amps. Now, what I could do is I could say that I'm going to use these new tables that we have. Now, if you do selective coordination, I've talked to consulting engineers who didn't know that these tables even existed. We've had these around since the code started mandating selective coordination. You know, that got the that caused a lot of questions in the industry on how do I do this with circuit breakers, etc. So most of your manufacturers are going to publish selective coordination tables like this, which our tables, the Eaton tables, go across the top is your line side breaker. That's your upstream breaker. Down the left-hand side is your load side breaker. And so in this case, I have a BAB20 downstream of an F-150, and I know, based upon testing, because our tables are done, are put together by testing pairs of circuit breakers. I test an F-150 upstream of a 20 amp BAB, and I keep putting in current until they both open. And I know that point is actually around 1500 amps. So for the sake of this example, I know that my BAB will selectively coordinate with an F-150 upstream up to 1500 amps. So I can plot that value on this trip curve, and I can show that since my fault current is 1000 amps, it's less than the 1500 amps. I selectively coordinate at 1000 amps. So I can effectively say now that I do selectively coordinate when the fault current is 1000 amps. But what happens when my fault current is greater than 1500 amps? In this case, 2000 amps, or it could be 10,000 amps. I know based upon those tables, because remember, the tables that we publish tell you the current value beyond which they're both going to open. So for a 2000 amp fault or a 10,000 amp fault, whatever the fault current is greater than 1500, I can tell you a very high level of confidence they will both open. So I separate this curve into region 1 and region 2. Region 1, I can effectively say these selectively coordinate when I have currents that are less than the instantaneous pickup of the upstream overcurrent device based upon the TCC curve. I know that for a fact because my fault currents, I can use the time current characteristic curve for both the downstream and upstream when the fault currents are in this region of the time current characteristic curve, and I can use the curve to tell me the performance of those devices on that current. When my fault currents are in region 2, greater than the instantaneous pickup of the upstream device, I need some other tool to help me figure out what the clearing time is and whether or not these will selectively coordinate. The good thing for power systems engineers is we have selective coordination tables that you can use to give you that point that you may look at a trip curve and say, well, I know based upon the TCC curve, it doesn't look like they selectively coordinate, but I have this table of tested pairs from the manufacturer telling me they will coordinate up to this value, which is into the instantaneous region, but I know it works because they're published data. So the answer to this one really is maybe. And the primary reason is because I didn't give you the fault current that both of those devices would see. You need to have the fault current plotted on the TCC curve. So I'm going to take a look at some of the chat window here. I see some discussion going about three-phase or phase to ground. Selective coordination for all currents and all times. You must use three-phase fault current and ground fault. That is correct, Joe Pavia. You have to use both, and sometimes the ground fault current will be greater, depending upon where you're at in the power distribution system. They both have to coordinate. Do long time, short time, and instantaneous have defined times? No. The long time, short time, well, let me take that back. Your long time, your long time pickup, let me get long time pickup for those who don't understand what I'm talking about. That will be this, oops. Hold on. Pen, yep. Let me maximize this and we'll just walk over this curve real quick. So this this portion up here is what we call the long time pickup, and that's on a molded case circuit breaker. That's the handle rating. Sometimes on electronic trip unit that'll be adjustable, but that data point there is what protects your conductor. That's what we size. That's what when we size our conductor for the load, we will pick an overcurrent device. That'll be the handle rating or the long time pickup setting. What I'll do is I'll go over that when I have an electronic trip unit, because on a thermomagnetic breaker, you really don't have any adjustability. You have the instantaneous region, which is this down here, and then you have your long time pickup. Everything else is basically driven by the construction of the breaker itself. Those are a thermomagnetic, and if you, I'm going to be posting for next week a circuit breaker basics class where we're going to talk about how that curve is constructed. So And that is what the long time pickup is, and that's what the instantaneous is. Now, the red breaker here in reality curves over underneath like this in some way, and this one will curve over like that. You don't see that. We don't normally publish that information, but we rely. You don't necessarily need that. You really want to rely on the tables that the manufacturers publish. But remember, the tables only apply to that manufacturer's devices, equipment. Now, we do have, from an Eden perspective, we have tested our fuses downstream of our circuit breakers, so we can give you some breathing room. Because remember, if you think about it, go back to that other example. If I have this breaker and I know these will coordinate at 1500 amps and I have more than 1500 amps, how do I fix that problem? So if I have this problem, I can do one or two different things. I could try to reduce the fault current. So if my fault current is up here, say I've got 1,000, 1, 2, 3, 4, say about 5,000 amps. If my fault current's around 5,000 amps, I have two options in front of me. I can try to lower my fault current to some value that gets it into this region over here. Okay. How do I lower fault current? I can tell the electrician to take a couple laps around the building with the conductor before he lands it on that downstream breaker. I could add a 1-to-1 transformer. The transformer, we saw that yesterday from a short circuit perspective. You add a transformer, that is one big hunk of iron that will add a big impedance, and it will knock your fault currents down considerably. And I have a very good chance of being in this region of my trip curve. Or my other option, which that's expensive, right? You're going to add a transformer. That's not cheap. That's gonna take some space, physical space, to put the transformer. You're going to need a primary and a secondary overcurrent protected device. All kinds of good stuff that's going to happen there. Or I can increase the size of this breaker and move the instantaneous further to the right. And I could use the tables to help me pick the right circuit breaker to get that done, because I can go to that table and find where the pairs have a fault current value beyond which is less than or is greater than my available short circuit current. So those are two options. I can increase the size of the overcurrent device. Now, the problem that you'll run into if you try to increase the size of the overcurrent device is right up here in the long time pickup. Remember, this breaker is this guy right here, and there's a conductor right here that I'm protecting. If I increase the size of this breaker by say from a 150 to a 250, or maybe I have to put a 400 amp breaker in there, I may be into an electronically actuated device, but I might not be able to adjust my long time pickup low enough to protect that conductor. So that means I have to increase the size of that conductor, which means if I've done this, if I find this problem after I've already pulled wire, that could be ungood. I might have to increase the size of my conduit. I'm definitely going to have to pull new wire. I am presented with a challenge, which is lesson number 1. You want to be pretty sure in your design phase how well these selectively coordinate with each other. Another solution is to say, look, I'm going to apply a fuse downstream. I've always pictured fuses in my mind as a device I put in my service entrance equipment because I've got 200-some thousand amps. I never really realized the importance of putting the fuse downstream closer to the load until you get into this discussion of selective coordination, because what you get when I put a fuse downstream, I get a very fast acting device downstream, which means I clear that fault. And if you were in my class yesterday, you'll remember, instead of seeing all of this 1, 2, 3 cycles, that fuse is going to make my upstream device see something like that, a little blip on the chart. The upstream breaker, that fuse is going to go so fast, that upstream breaker is not even going to know what happened. And the value of that is I don't have to change my F-150. I love my F-150. I want to keep the F-150. I know it fits in that panel board. If I increase the size of the F-150 to a 400 amp, it may not fit into my panel board anymore. I have to change the panel. It may not protect the conductors. I got to increase the conductor size. That putting a TCF Busman TCF fuse downstream of that breaker lets me keep a 150 amp breaker upstream. It'll selectively coordinate up to the interrupting rating of that upstream breaker, which gives me a lot of room. That reduces the size of everything upstream. If I can do at least one layer of that fusible solution downstream, this table shows you the testing results of what we've done with the QSCP solution downstream of our breakers. So that was an F-150. There's my F-150 column right here, okay? And I put a TCF, say I don't know, somewhere over here, say a TCF 30, or TCF 30. I selectively coordinate up to 35,000 amps. That's humongous. That is a lot of breathing room. That fuse, now what that'll do, a couple things, it'll help me reduce incident energy, because I'm going to take that bolted fault current out up to 35,000 amps. But if I have an arcing fault, that circuit breaker, the chances of me having my arcing current in the instantaneous region of that circuit breaker are much greater, because I'm not worried about pushing the instantaneous to the right because of a downstream slower device. I've got this fast acting device downstream. If you love breakers and you're not a fuse guy, you will want to consider this to help you achieve your selective coordination goals and reduce the footprint and cost of the overall design of the power distribution system. We can selectively coordinate all fuses, we can selectively coordinate all circuit breakers, but when you have a healthy mix of both of those technologies, it's like the right recipe. Like Anna Marie Albagetti, the Good Seasons lady. It's in there. It's going to be a good solution. So I don't have to increase the upstream overcurrent device and all that good stuff. So a mix, the message there is design tip number 2, consider a healthy mix of overcurrent devices in your power distribution system design. It can help decrease incident energy, increase reliability, and give you the best of both worlds in many applications, and bail your butt out of a problem should you have missed the selective coordination requirements up front. So that is a very important, but hopefully you're seeing, if you've not seen TCC curves before, hopefully this is giving you some insight as to the value of what you're looking at. Okay, it is that third dimension to understand what's going on inside of the picture. So a couple questions. Let's go to the chat. Remember, circuit breaker testing for selective coordination are set at their max settings. That is true. So when we talk about the tables that we have, whenever you see those tables, the settings for the breakers are going to be their maximum settings. It doesn't necessarily mean that when you start making adjustments in the long time region or your long time pickup, that you're still going to maintain selective coordination. So when you're dealing with circuit breakers, you're definitely going to have to be moving those curves around and getting a feel for at least the long time region, even if you're using the tables. All right, especially if if you've got other devices upstream and downstream. Good point, Mr. Pavia. Ron Shapiro, are there no current limiting 30 amp circuit breakers instead of the fuse? There are current limiting circuit breakers, but remember, the circuit breaker, the fuse is a very efficient device. It has no moving parts. You're not going to get anything that's more current limiting than that specific overcurrent device. We have not, I can't say that we've done a lot of testing with the current limiting breaker downstream. Not to say, even if we did, you're still not going to get that same level of performance that you can get out of that fuse. I will talk about current limiters, so let's get to question number 2 first. All right. Hopefully that question number 1, remember, you need to plot current. If anybody shows you a time current characteristic curve and there's no current on there, your first question out of your mouth is, what's the fault current? Number 2. Now this is going to be a fun one. When selective coordination is your design goal, OCPD 1, which is this guy right down here, OCPD 1 must selectively coordinate with, and that was a question. Let's go to the results. I got to go to the results. When selective coordination is your design goal, OCPD 1. All right, so, and I would say design goal or code requirement, doesn't matter. All right, here's what we got. 42 say device 5. 75 said devices 5 and 6. 3 said device 6, and 8 said they don't know. Well, let's take a look at it. I'm going to walk you through the answer to this one because you 76 of you, I think, are pretty sharp cookies. 42, I don't know, maybe that was your gut reaction. And the other 10, so 76 out of 129, you're on board. Still not a good passing grade for everybody, but we're going to walk through this. Here's whenever you want to determine what devices you need to selectively coordinate, always ask yourself this question. If I open both of these devices, do I lose the same load or do I lose a different load? Now let's do this with device number 1. If device number 1 opens and device number 5 opens, what do I lose? I also lose 4, 3, and 2 because I take out more of the system. So I don't want that to occur. So OCPD 1 and OCPD 5 have to selectively coordinate with each other. So this one and this one must selectively coordinate with each other. Now let's walk through the next one upstream, device number 6. If I lose 1 and I lose 6, I lose this whole panel board's gone. So definitely 1 and 6 have to coordinate with each other. So the answer to this one is 1 and 5 and 1 and 6. They have to selectively coordinate with each other. Now, I'm going to go over the challenges of working through how I coordinate device 1 with number 6. That's another one of our questions. But suffice it to say that the right answer to this question is, and this was just me talking about that, the right answer. So this just walks through the same scenario that I just walked through. The answer to that was B, devices 5 and 6. So that's an important, 1 has to coordinate with 5 and has to coordinate with number 6. All right. So 77 of you did a very good job. Thank you. And let's move on to question 3. When selective coordination is your design goal or code requirement, OCPD 5 must selectively coordinate with, now we're talking about 5, right? We said we have to address, what do we do? What do we have to coordinate with 5? Let's take a look at what our respondents said. After that last question, we lost 2. So we had 132, and then we went down to 130. I don't know. I think somebody just couldn't handle it. All right. So 22 people said device 6. So 5 has to coordinate with 6. 66 people said devices 1, 2, 3, 4, and 6. 36 people says devices 1, 2, 3, and 4. And 6 people were not sure. Okay. The 36 people that answered devices 1, 2, 3, and 4, love ya. You got it right. The rest of you guys, hang on. We're going to show you why. Okay, so here we go. Again, ask that question. 5 and 6. If I lose both of those, what loads? I lose the same load. If I drop 5, I lose breakers 1 through 4. If I drop 6, I lose breakers 1 through 4. So I don't have to worry about selectively coordinating 5 and 6 because they take out the exact same load. I do have to worry about selectively coordinating 5 with all of these downstream. Now here's what we typically do. We will pick the largest device. So if, for example, if just for giggles, this was a 20 amp device, this was a 100 amp device, this was a 15 amp device and this was a 15 amp device, I would make sure that I coordinate with the 100 amp device with this main device only. I know if those two work, all of these other devices will selectively coordinate with each other. I only worry about the largest downstream device when I'm looking at this coordination. The key message here is I don't have to worry about the coordination between 5 and 6. All right, these next two slides basically just talk about exactly what I just said in writing. So the answer to that question is you have to selectively coordinate with devices 1, 2, 3, and 4, and that is it. All right, I'm seeing some dialogue on YouTube. The question was, is the fuse going to operate in the current limiting region down at the 1000 amp fault level? And Dan Neeser noted that the fuse becomes current limiting where the clearing time of the fuse is faster than 0.01 seconds. So when the fault current is increased to a point where my fuse curve crosses 0.01 seconds, I'm entering the current limiting region. Let's take a look at it's because of lunchtime limitations, 1 hour. Okay, I don't know what that was about. Maybe it's because that's why they didn't get so many questions done. But in any case, let's take a look at question number 4. Question number 4, if the short circuit in the load side of the panel is 2082, what amps will device 6 see during this fault current? So let's take a look at what the answers came in at. I don't know about you, but I'm loving this Menti thing. All right, so we have 15% of the respondents noted that 2082 amps, that device 6 is going to see 2082 amps when there is a fault on the secondary of 2082 amps. 64% said 902 amps, 8% at 694, and 13%, what are you talking about? Well, what I'm talking about here is the fact that we have a transformer in the picture and the transformer doesn't cease to do its job when there's a fault downstream. I have to consider the reflection of the current from the secondary side to the line side. So I'm not sure the right answer here myself, so let's do this. We're going to take 2082, we're going to multiply that by 208, and we're going to divide that by 480, and I get 902.2, so the right answer is 902 amps, which was 65% of the respondents. So you guys feel good about yourself there because you got that one right. 902 amps. Remember, a transformer transforms energy on one side to the other. There are basic equations that we use to understand when there's a current on the secondary, what is that current equivalent on the primary? And we do that based upon the math of the turns ratio. I2 is equal to the N1 over N2, the turns on the primary, the turns on the secondary, times I1. And so we basically have to do that math to reflect currents back and forth. And that's basically, remember, we had that curve very early on in this presentation that talked about the reflecting of the curve from line side to load side because of these turns ratio. You'll see, we'll plot everything at the same voltage, but not all of those devices are at the same voltage in the power distribution system. We will move those overcurrent devices to the same voltage based upon the turns ratio. That will impact the trip curve. So, for example, I1 is equal to I2 times the secondary voltage over the primary voltage. I2 is the primary current times the primary voltage divided by the secondary voltage. And I always use the line to line. If you use line to neutral, it would work out. Just make sure you're using the exact same numbers when you do that. You know, me and the square root of 3 in college didn't get along. I'd go to parties, he wouldn't show up. Square root of 3 would sometimes go to the party and I'd stay at home. So I always was forgetting that square root of 3 and using it where I wasn't supposed to. But that's basically the math right there. If I know my secondary current's 100 amps, my voltage on the secondary is 208, my primary voltage is 480, I can do the math and reflect the current to the primary. You're going to understand the importance of that when we start looking at selectively coordinating around a transformer, which nobody really talks about in the industry. So in that case, I had 2,082 amps on the secondary. I reflect that up based upon the turns ratio, and the primary device will see 903 amps. All right. So if I put a meter in that secondary, I would see 2,082 amps, but I would only see 903 amps on the primary. Yeah, and Don Gannier, you're right, Don. And I've had you say that to me multiple times. I've had other people say that to me. Mike Holt told me that. You know, me and the square root of 3, I found a new love there, and I have to make sure I always keep that square root of 3 in my pocket, else I will screw that up. These are the equations that you're going to want to know and memorize for a lot of different applications. I'm including them here as well, how to get the full load amps. You know, full load amp calculation. I did a class one time, I had 80 some students in the class, and we were talking about transformer protection. And I said, okay, the first step in anything, you're gonna have to calculate the full load amps. I had 5 people in the class that knew how to calculate the full load amps of a transformer. I'm gonna probably do a live stream on that one too, because I think it's very critical. These are the equations that you use, kVA over kV, basic information to calculate full load amps. All right, so and again, this is just, I probably have too many slides in on that one, but 902 amps is the right answer. Good job to a good percentage of you on the call. We are pushing the limits of WebEx. We have 98 on YouTube. We are rolling. Question number 5. When selectively coordinating fuse installations, I have to first calculate my short circuit currents. Let's see what we got. 87 said true, 26 said false, 17 aren't sure. All right, for you 87, I'm going to teach you another tool, because I'm learning that there are a lot of design engineers and even those who deal with selective coordination that don't understand the fuse ratio tables. I'm going to teach you a trick, and you are going to just thank me, and you're gonna not sleep tonight, because you're going to be thinking about how you're going to use this new tool to help make your life easier. If you think about when I have 2 fuses, so in this example, I have a 600 amp LPJ fuse upstream of an LPJ 300. When the fuse industry has had this selective coordination ratio tables for many years. And those tables make your life easy, because as long as I maintain a ratio based upon the published ratio tables of the fuse manufacturer, and I'm using their fuses, I mean, it's not someone else's fuse downstream of my busman fuse. As long as I'm using our fuses, I can maintain a simple ratio, and I don't care what the current is that passes through them. I can have up to 200,000, whatever the interrupting rating is, pass through both of those fuses, and I will be sure that that 300 amp fuse will open and the 600 amp fuse will not. Now, these fuse curves still have the same regions. They have a region 1 where I can use the TCC curves, and if I'm not using the tables, if I'm not using the selective coordination ratios, and I'm simply using the TCC curves, I know the performance of these as long as my fault currents are in that region. The moment I go and I have fault currents that are greater than the current limiting region of these fuses, and remember, the current limiting region is where those fuses cross 0.01 seconds, that's way down here. Any fault current greater than that point on the TCC curves, so for that downstream fuse, any current greater than that point, I'm in the current limiting region of that fuse. I know that when I go above into region 2, I have fault currents greater than where they cross 0.01 seconds. I need some other method, and the ratio tables are what you use. So these tables show you that as long as I have the right pairs of devices upstream and downstream, there's my 2-to-1 ratio. So if I have a 20 amp fuse downstream, I can have a 40 amp fuse or greater, and I'll selectively coordinate for any current you put through them up to their interrupting rating. And some of these fuses have a 300,000 amp interrupting rating. So I don't have to worry about fault current. If I'm maintaining a ratio, I just simply maintain that ratio throughout my power distribution system. I have 200,000 amp short circuit current rated equipment. I have 200,000 amp interrupting ratings. The only thing that I'm going to need fault current calculations for are probably incident energy reduction to do an analysis to see what my arcing currents are. And we're working on tools to make your life easier there too. So there's I had my two LPGJs, I had a TCF fuses. If I have those fuses upstream and downstream of each other, I maintain a 2-to-1 ratio. I'm good every day of the week, twice on Sunday. I don't care what the fault current is. So as long as I'm maintaining my ratios, I don't have to calculate fault currents. And if I nest these things together, I can have in the first case, I have a 100 amp fuse downstream of a 400 amp fuse. That exceeds the 2-to-1 ratio. I definitely selectively coordinate for any fault current passing through them. I have a 400 amp fuse downstream of an 800 amp fuse. That maintains a 2-to-1 ratio. I am selectively coordinated for any fault current up to the interrupting rating of those devices, which is 200,000 amps. Makes your life very easy. The selectivity ratio guide tables, I will have a link to those. In my YouTube channel, there's a link, and I will provide those that information to anybody who needs that. Every manufacturer will publish those ratio tables. Fuse applications do not require calculation of short circuit currents, so ratio tables give you that, and the answer to that one is false. I don't need to calculate short circuit currents to do a selective coordination study on a fusible system. It's an advantage that the fuse has. Every overcurrent device has an advantage, and this is indeed a big strength for selective coordination. I've talked to some firms that do design build, and I asked them, what is the software that you use? Do you use SKM, EDSA, Easy Power? What do you use? And they said, well, we don't use any of that. And I said, well, how do you design your systems for selective coordination? And I get that blank stare. They don't quite understand the selective coordination methods and what we're talking about here. So, if you're not using any type of software to do your selective coordination studies, you probably should be using fuses and maintaining 2-to-1 ratios. Most of your large design firms and whatnot have people on staff to do this, but it's important that you pay attention to that, especially if it's a code requirement and if it's a design goal of your customer. All right, question number 6. I got to check, make sure I'm doing good on time. All right, it's 1 o'clock. We got time. Good. Let's do question numero 6. Here we go. When selectively coordinating circuit breakers, I have to calculate the available short circuit current. All right, let's go to this puppy. All right, so the 30 who answered false on that fuse one, good job, buddies. When selectively coordinating circuit breakers, I have to calculate the available short circuit current. All right, we got 112 people that said yes, 12 said false, 10 not sure. So overwhelmingly, we understand that yes, you do have to calculate your fault currents. That's one of the key things with a circuit breaker. They are sensitive to the amount of fault current, and we talked about this in the very first example. I showed that BAB20 downstream of an F-150, the circuit breaker, not the truck, and we understood that I need to plot my fault current. I know that as my fault current increases and into the instantaneous region of both of those overcurrent devices, I'm going to end up needing some way to address that problem. The tables are very important to help you understand the performance of those breakers. Any of these devices that you see in this upstream, all of those are based upon their maximum settings. Just because I'm using the tables does not mean I don't need to plot those devices. I'm going to be looking in the overload region. I may have to add some delays. I may have to move my long time pickups up or down to protect my conductors, or I may have to move my short time pickups up to provide breathing room for my motors to start. And we're going to talk about that as well. But these tables will give you the performance of your overcurrent device when those fault currents start to inch into the instantaneous pickup region of the upstream circuit breaker. Remember, now I'm showing the 15. Now, if I said, that 150, I have 2,000 amps. If I increase that breaker upstream to a 225 amp thermal magnetic breaker, I can go up to 2,200 amps. So now if I had 2,000 amps of fault current, I increased to 225. Now, what does that mean? That means I might have to actually increase the size of my conductor. I'll have to possibly increase the size of my panel board, etc. But there are some challenges there. Now, so remember our tables, and this is just regurgitating. And since most of you got this right, and we went over this in the beginning, I'm going to walk through this. I usually do a deal whenever I use Mentimeter in my classes. If 90% of you get it right, I don't go through the answer. But if you get it wrong, we're going to go laboriously through the answer. So that answer was true. Take a quick look at the chat. I'm going to take a quick look at the chat here. So let's take a look. So what is the typical service life for fuses, and how long can they be in service and still be expected to meet their protective characteristics? So here's the thing with a fuse. I've heard people talk about fuses being when they see a large fault current like that, and what does it do to the elements that are inside and things of that nature. What you really need in a fuse to hurt that element is you need high fluctuations of a longer period of time in current flow to drive a lot of heat high, a lot of heat low, and whatnot. You need those fluctuations. These short circuit currents, in my opinion, from what my experience has been, they don't provide enough heat and energy to weaken that element of that upstream device. I don't know. I know I have some other busman individuals on there that might be able to add a little bit to that to the chat session, but I know the YouTube guys don't have that access to the chat on the WebEx side of the business. But that was a question, and really to hurt that element, you have to have a very high heat fluctuations, which is pretty rare in a power distribution system. But in any case, I've never experienced any issues with in my history with fuses that are at a customer's location where that had been a critical issue from a coordination perspective. Presented a challenge there. Selectivity ratio, where is it located? I already answered that one. All right, so it looks like I think I'm up to date on that. Let's get back to the program. Question numero 7. Here we go. Are you ready? Question 7. Zone selective. Oh, I love this question. Zone selective interlocking is a way to achieve selectively coordinated systems. Oh, let's see what we got on the poll. 134 people, 88 say true, 32 say false, and 14 say, what is that? Okay, this has been, I used to watch people do presentations, and I would hear them say, you have to get selective coordination with circuit breakers, you have to do zone selective interlocking. And that could be no further from the truth. The answer to this one is false. So 32 of you got this right. 88 of you, I'm going to changing the world here. So I'm going to at least have 88 people understanding zone selective interlocking and why it does not get you selective coordination. And I think the problem with why people always answer that is because of how we teach it. So let's walk through. Zone selective interlocking came into the picture many moons ago, well before I came into the industry. I can remember in the 90s when I first came to work for Eaton, I would take technical calls and I would answer circuit breaker questions, and zone selective interlocking was a topic back in 95, and it was a topic even before that. There are IEEE papers written on this. It was introduced to provide a level of protection for equipment when there's a fault inside of equipment. So your heavy industrials used it. Your big petrochems and other examples like that were worried about protecting equipment. This was what we did to help provide a level of protection because it provides a faster acting solution when faults occur in the zone. Now, when I have two protective devices that are zone selectively interlocked, which means I have little wires that go in between these two. And there's a voltage signal. I'm going to say 24 volts. Whatever. I'm not going to say 24 volts. You didn't hear that. What you heard was there's a voltage signal. It'll vary by manufacturer, the magnitude and DC versus AC, all that good stuff. I'm not going to get into that, but that voltage signal, basically what it does is it lets the two devices, it lets each other know that they both see a fault occurring downstream. And when they both see a fault occurring downstream, this guy up here is going to basically go based upon what you have programmed into the trip unit. This guy down here, the downstream, will trip based upon what you have programmed into the trip unit. It doesn't change those set points for a fault downstream. Now, in a selectively coordinated system, you're going to have a device that's probably downstream of this. There will be a little jumper on itself inside here so that it's not looking for a breaker downstream in a zone selectively interlocked system. So it doesn't automatically go instantaneously because you want to coordinate with a downstream device. But these devices are going to go as they're programmed. If you didn't program those devices, you could have overlap in the overload region and they will both open. If you have a fault higher than the instantaneous pickup of both of those devices, and the tables tell you they will both open, they are both going to open. I don't care if they're zone selectively interlocked. When there's a fault downstream of both of them, they go as they're programmed. You don't defy the laws of physics and say all of a sudden that upstream device is going to hold its contacts closed while the downstream opens. They will respond based upon the selective coordination tables and their time current characteristic curves. Now, the value of zone selective interlocking is when a fault occurs in between. Because here's what happens. These two are wired together, remember, and there's a little voltage signal. When the upstream device sees that fault, he's going to say, or she, I'm not going to be gender specific on these breakers, this breaker is going to say, I see a voltage signal or I don't. If it doesn't see that voltage signal coming from the downstream device, it knows that the fault is in between those two devices, and what it will do is ignore the settings that you have programmed into the faceplate or ignore the settings that you've programmed into the electronic trip unit, and it will trip without an intentional delay. Now, when I say without an intentional delay, what I mean there is that without intentional delay, it's not going to be as fast as the instantaneous, because think about what's going on. There's a brain in this guy up here. Unlike there's no brain in the guy on this side of the computer, but there is a brain on that device. And the brain has to say, I see fault current flowing. It has to look at the input signals to see if there's a device downstream. If all of that happens, then it tells the breaker to trip. That usually takes around 0.07 seconds. Just about 0.07 seconds for all of that to occur. And that device will then open. It's still considered without an intentional delay, even though you have 0.07 seconds, but it's still faster than possibly 30 cycles if that's a power breaker or some other time delay that you have programmed in, because what selective coordination does for it, it makes you put an intentional delay upstream. So if anybody ever asks you, what is zone selective interlocking for? It is not to achieve selective coordination. I don't care. It's not in the overload region. It's not in the instantaneous region. It's not in the short time delay region. It is in no region. It is there for arc flash reduction when the fault occurs in the zone of protection. Hopefully, those 88 people will understand that. All right? Okay. All right. I think I just did all of that, and I didn't have the presentation mode on. Well, that wasn't smart. Technical difficulty. And I'm not going to go through all of that again. Remember, zone selective interlocking is zone selective interlocking is not arc flash reduction, is not selective coordination. It is arc flash reduction. All right, so I'm just going to walk through this because I don't think anybody saw this before. So I have a fault downstream of both devices. They will both open if the fault currents are high enough. You get the benefit when you have a short circuit in between those two devices, and the clearing time is right around 0.07 seconds. And so the answer is false. All right. Ready for question number 8. And it is 1:22. We're doing good on time. Question number 8. Series rated solutions are inherently selectively coordinated. Boy, I can't wait to see the answer to this one. Series rated solutions are inherently selectively coordinated. 47 said true, 65 said false, 25 not sure, 137 respondents. This is like, what is that, Family Feud? It's Family Feud. It's better than Family Feud. TD Feud. Distance Network. What's the right answer? Remember what series rating solutions are. It's an upstream device protecting a downstream device. To do that, they both open. So the answer to this is false. Series rated solutions are not inherently selectively coordinated. In fact, they are the polar opposites of each other. A series rated solutions are leveraged when I want a downstream device to have a lower interrupting rating. So I need to make sure that I protect that lower device, which means my upstream and downstream are probably going to open for those high, well, they're definitely going to open for high fault currents. You know, fault currents in the overload region, I can have coordination. So if I was doing, say, if I was doing a 0.1 second coordination, I could have a series rated system be perfectly fine in a healthcare application because they're doing 0.1 seconds. They're not worried about the high fault currents, and they're only worried about overload regions. I wouldn't recommend that, but that would be meeting that, but it would not meet the selective coordination because you got to consider those higher fault currents. There are two methods when you're applying these devices. You have a fully rated protection and a series rated protection. Selectively coordinated systems are fully rated. Right? Fully rated, 65,000 amps. I have 31,000 amps available fault current at this bus. All devices can interrupt it. A series rated system, the downstream devices can have a lower interrupting rating than the available fault current at that bus. So, my Siri is talking. So, when I have a series rated system, I have a 10,000 amp interrupting rated device downstream, and I have a 65K rated device upstream, and I have 31,000 amps available. They're both going to open. All right. The other thing you've got to consider, and we talked about this yesterday, motor contribution is very important when you're doing a series rated system. It can't exceed 1% of the interrupting rating of the lower rated circuit breaker. This is something that is missed by most design engineers is missed by most engineers because they forget about that 1%. If you have motor contribution downstream, not only aren't you going to be doing it for selective coordination, you're not going to be doing series rated systems because of that motor contribution. And yeah, you're going to have to pay a little bit more for that breaker downstream. So the answer to this question, series rated solutions are inherently selectively coordinated. The answer is false. So for the 66 that said false, congratulations, pat yourself on the back, do a victory dance, stand up, jump around don't hurt anybody, jump around the room. For the 48 that said true, don't worry, don't hold your head down too low. It's going to be a good day. Still, you have about a few more questions to go. And for the 25 that's not sure, hopefully I was able to share something with you and you learned something new. All right, quiz question number 9. This is where it gets good. For this example transformer application, what short circuit current do we use when selectively coordinating circuit breakers B1 with B5? No, we're not playing bingo. We're talking about selective coordination. What fault current do we use? Let's see what the survey respondents said. Out of 130 respondents, we've got 2,776, 8,324, 1,203, and I don't know. It's always good to throw a B in there every now and then. You know, I'm a musical kind of guy. You got to have a good B. So 1203 amps is not right. 8327 is not right. The 2776 is the right answer for that. So it looks like a majority of everybody outside of the 47 that don't know, we're doing pretty good with regard to the answer on this one. So I'll just walk you through. What you're really looking at is the infinite bus. Now, you don't necessarily have to use the infinite bus solution on the secondary. You can, and we talked about infinite bus calculations yesterday. The YouTube video is down below, and there's also another separate video on my site which just talks about what is infinite bus. You don't necessarily have to use the infinite bus because the primary current available from the system is probably going to be lower than infinite bus. It will definitely be lower. But in reality, as we talked about yesterday, lowering that fault current at the line side of the transformer really doesn't change the fault current on the secondary all that much. If you need a few amps to get your coordination numbers to work, you might be able to get it. But if you need thousands of amps, you know, going lower than infinite bus, assuming the actual fault current on the line side, probably not going to get you out of hot water. But basically what we're doing is we're calculating the full load amps on the secondary, dividing that by the impedance of the transformer. Don't forget the 10% lower impedance. And we're calculating the infinite bus calculation. In this case, I did not do the lower 10% because I wasn't thinking about it when I was doing this slide deck. But I should have, and I will correct that for later. So the right answer is 2,776 amps. So majority of you guys got it right. And hopefully those who got it wrong understand that we're using infinite bus calculation. If you don't know how to do that, check out a few of the other videos that are on my channel and also the streaming recording from yesterday. All right, question number 10. Here we go. For this example transformer application, what short circuit current do we use when selectively coordinating circuit breakers B1 with B6? Now, I want to make sure we're clear what we're talking about. B1, and we said this earlier, that B1 does have to coordinate with B6. Now, the question is, what current do we use to selectively coordinate those two numbers or those two breakers together? Let's see what the respondents said. Drum roll, please. I need audible. I need somebody who knows how to do the audible stuff. I'm going to need like these little clicker that gives me audible. 32 said 2776. 13 said 8,327. 44 said 1203. And 39 said, can I phone a friend? No, you cannot phone a friend. Sorry about that. You're stuck with me and those on the chat session, which I haven't been looking at chat, but I'm going to look at it after this question. Thank God I'm not looking at chat. Anyway, so let's walk through the numbers. And basically what you're going to do here to understand what you have to selectively coordinate to, you have to understand the turns ratio and the fact that a transformer doesn't quit working just because there's a fault downstream. It's going to do its job. It's a very reliable employee inside of your facility. That puppy works night and day. It's a hot environment and it just keeps working. So I'm going to walk through these calculations again. I know that the infinite bus on the secondary is 2776. I can tell you if you said that as an answer, you were not right. So the 2776, 34 people, sorry. Better luck next time. That's not the right answer. So let's keep walking through this. Now, if I reflect that current to the primary, so remember, I have a fault on the secondary. It's 2.8 kiloamps on the secondary. When I reflect that to the primary, it's 1,203. So when I have a fault on the secondary of this transformer of 2,700 amps, it's only going to see, the primary breaker is only going to see 1,200 amps because of that turns ratio. So those who said 1203, the 45 people out of 132, pat yourself on the back, jump up. You know, you've earned your keep. Don't stop watching. You gotta stay on. You gotta stay on because you gotta stay on. But the 2776 guys, sorry. Better luck next time. In the 8327, I don't know where that. I think I threw a square root of 3 in there somewhere. You didn't quite get that one right. So the right answer is 1203. Whoops. I don't know what I just did, but I did something. So B1 has to selectively coordinate with circuit breaker B6 up to 1203 amps. Now the downstream breaker is going to see more fault current, but it's the upstream breaker, and when that current goes into the instantaneous region, that I have to worry about the selective coordination. So the right answer to that was 1203. Those were the 10 questions that we had. It is 1:32. I'm going to check. We're going to still go on, but I'm going to check the feed. Let's do a. Okay, I'm going to take a look at. I'll take a look at this chat session. Let me scroll up a little bit. We'll have to increase cables. Where's the selectively ratio? Okay, we already talked about that. What is the typical service life for fuses? I already talked about that. We'll have to increase cables. If you don't need to know the short circuit current for fuses, how do you know what fuse to use? Okay, you size your fuses on what you are protecting. So if I have 300 amps worth of conductor, I'm protecting it at 300 amps. I'm not picking the fuse based upon the interrupting rating. I'm picking the fuse based upon my ampacity of the conductor that I need to protect per Article 240 of the National Electrical Code. I'm picking my fuse based upon if a transformer primary fuse or circuit breaker. I pick circuit breakers and fuses because I need to protect something. Conductors, I calculate the ampacity, I pick my overcurrent device. Transformers, I calculate the full load amps on primary and secondary. I go through my multipliers, 1.25 up to 2.5 on the primary. I follow the requirements on transformers from the National Electrical Code, and I pick the overcurrent devices that I need. And that's how I pick the devices. The only time I'm doing a comparison on short circuit is when I'm worried about short circuit current ratings, or I'm worried about interrupting ratings, or I'm worried about selective coordination. And if I'm using my fuse 200,000 amp short circuit current rating, can't get anything higher than that. So I'm not worried about short circuit current rating. Interrupting ratings, can't get anything higher than that. So I'm not worried about interrupting ratings. Selective coordination, 2-to-1 ratio, I don't know. Arc flash, maybe? I would say arc flash, you need to do that analysis. Let's take a look on YouTube. I got a screen behind here. Is the fuse going to operate in the current limit? We already talked that one. Dan Neeser answered that one. Thank you, Dan, for tuning in. Do you have a table for molded case circuit breakers and insulated case circuit breakers showing the internal fixed magnitude instantaneous override? Yes, we do. Carlos, I will put a link down. We have a consulting application guide. If you go to eaton.com/consultant, www.eaton.com/consultant, you'll have access to our consulting application guide and a lot of other materials that are available to you. And we have our selective coordination tables, which I will put in the link below this this YouTube video. If you're interested and want to learn a little bit more, you can reach out to me. I can answer emails, or you can reach out to your local application engineer in your jurisdiction, your Eaton application engineer. We have application engineers across the country that are tons smarter than I am on a lot of different things. And they will help you put your system together. They'll help you engineer a system that will work to your customers' wants and needs. And they'll get into all the technical details. So very important to connect with your local sales office. You can find out who the right people are through your distributors, your Eaton distributors as well. But I will put those tables out. Low voltage fuses, okay. Low voltage fuses are susceptible. Medium voltage fuses. So we got Chandak, Mahesh. Thank you. There's some answering. If you don't need that, we talked about that. For loads that cycle on and off, what is the typical life of a thermomagnetic circuit breaker? Again, when you get into typical lifespans, it's really hard because there's a lot of things from a condition of use perspective. I mean, it depends on where the breakers are, where the fuses are. Are they inside? Are they outside? Are they in high humidity, low humidity, and they're in a hazardous location? Are they being, there's so many things that impact the life of an overcurrent device. I sit on NFPA 70B, and we're having these discussions on what you can do to perform general maintenance on equipment, but I'm not going to get into how long will they last. Question 10 answer is not correct. Question 10 answer. Let's go back to question 10. I love this. 1203. We got a not correct. Let's do the math. So 2776. I could have been wrong on my math. 2776 is the secondary current. We multiply that by the secondary voltage, 208 times 480 divide 1202.9. It's 1203 if I do the turns ratio. So the short circuit current we use when selectively coordinating circuit breaker B1 with the primary is indeed 1203. Okay, when does the selective coordination get submitted to the AHJ for the record and approval before, during, after the job? Here's what my suggestion is. Before the job gets started, the inspector and the designer need to have a level of understanding, an agreement as to what are you looking for from a selective coordination perspective. We have a form which I'll share at the bottom of the link that is basically a form that basically the design engineer fills out that says, I'm going to meet Article 700 requirements, 701 requirements, 708 requirements. It might be a healthcare application when they're doing 0.1 seconds. The engineer should tell the inspectors, here's what I'm planning to do. And then if there's an issue with what they're planning to do, you need to have that discussion before that job starts. I have some slides that talks about the process of selective coordination and what we do. And a part of that process is the design phase. We will need to quote a job, right? We haven't broke ground yet. I don't know what I'm going to buy. I'm going to have to make some basic assumptions to make sure that when I quote you a job, that number is going to be real. And I don't have to come back and give you different pricing because we're changing the design criteria. Establish that performance level up front. In the power distribution system with the design engineer of record. That's going to be critical to avoid problems later on. Let's see what else we got. No, sorry. B1 has to coordinate up to 1203. Sorry about that. Yeah, I don't agree with that answer. How about the interrupting rating of the fuse? 200,000 amps. And again, the fuse rating, we have voltage, it's rated for 200,000 amps at 600 volts. So if I use it at a lower voltage, the interrupting rating is not going to go down. Your interrupting rating of a fuse is at its voltage on most of these fuses. If it's a 600 volt fuse applied in any system downstream, its interrupting rating is whatever I publish at 600 volts. Now, on the circuit breaker side, you'll have one breaker that will have different interrupting ratings dependent upon the voltage rating of the circuit breaker. So I can have a molded case circuit breaker have a high interrupting rating, 65,000 amps at 240 volts, but it could have 35,000 amps at 480 volts. You got to really read the instructions and understand the labeling of the circuit breaker. I'm going to have a breaker basics class next week. I'll have a fusology class coming up here shortly as well. I'm going to hit all the overcurrent. Hey, we're stuck in the house. We're stuck remotely. That doesn't mean we can't learn something new. All right, so let's talk a little bit about what I want to do next is I just want to move into 0.1 seconds because I know that's always a topic that comes up. And now that we have a lot of people on the phone that understand 0.1 seconds or understand selective coordination, we can now walk through and help you understand what we're doing in a 0.1 second world. And that is it's used in the healthcare world. And I have a separate PowerPoint for that. Hopefully this pops up right. Okay, it did. This is an older PowerPoint, but it still serves the purpose. So coordination in a healthcare environment. In a healthcare environment, basically in 517.17, this tells us that the ground fault, we talked about this earlier, this has been in there for a very long time, has to selectively coordinate has to achieve 100% selectivity. That's on the ground fault side of the business. But when you get into, now this is the 14 code and didn't change beyond that. I'm not sure. Yeah, no, it didn't change beyond that. 517.30, we may have changed the number in the 2020 code or the 17 code, but in any case, the way the language reads, it says overcurrent protected devices serving the essential electrical system shall be coordinated for the period of time that a fault's duration extends beyond 0.1 seconds. And it says the terms coordinated and the terms coordination and coordinated as used in this section do not cover the full range of overcurrent conditions. So let's talk about what that means. This is the NEMA's definition. I like what NEMA did in their application note on this. I'll put a link to this also down below. But let's walk through the definition from a coordination, because there's no definition really in the National Electrical Code or NFPA 99. It just sort of says what I just read. So NEMA's telling us that it's a localization of an overcurrent condition to minimize outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent devices and their ratings or settings. That is the same as selective coordination up to that point. Here is where things got a little different. Ensuring separation of their time current curves beyond a specified time period, the time period, without regard to fault current magnitude. So what does this mean? So without regard to fault current magnitude, and it says, or below a specified level of fault current, less than the maximum available fault current. So what does that mean? So let's take this this application here where we have two circuit breakers that are in series with each other. I have 20,000 amps. Now, based upon what you just learned, you know that with this situation, because the fault current is greater than the instantaneous pickup of both of these devices, you can safely say these are probably both going to open. Based upon what you see, you would have to say they will open. If you had selective coordination tables, then you could do an analysis to say, well, the tables that are published tell me I selectively coordinate up to whatever that number is, and if that number happens to be greater than 20,000 amps, then you can say they selectively coordinate. But based upon what we see, we would have to say these are both going to open. Thanks, Don. It's 517.31G in the 2020 code. Now, what 0.1 seconds tells you is separation of their time current characteristic curves. So you have to maintain separation, but I have a problem. I have an overlap down there. I call that the foot. That's the instantaneous region of both of these breakers show an overlap in the instantaneous region. These would not meet that language of separation of curves. So the NFPA 99 group and the 517 group say, okay, what you do is you basically hide what's below 0.1 seconds, ignore the overlap of the trip curves below 0.1 seconds, and you're looking for separation of curves in the time period above 0.1 seconds. And then you still have the problem, because now everybody on this phone is educated enough to know that even if I hide those, because that looks just like the BAB20 downstream of an F-150, the breaker, not the truck, right? So I would know, based upon that earlier discussion, that 20,000 amps going through these two breakers, I'm going to open both of these breakers. So we have to, without regard to fault current magnitude. So the way the code language reads is, you hide the overlap of the trip curves below 0.1 seconds, and you disregard the fault current, and you're looking for separation of curves above 0.1 seconds. So basically what they're doing is they are, I don't want to say they're only coordinating for the overloads. It is the overload region of the trip curve, but you could have fault currents down in that region. In that case, you would selectively coordinate anyway. But in any case, that's basically how you achieve selective coordination in 517.31G as per the 2020 code, but in the 14 code, it was 517.30G. Now, from a fuse perspective, again, you're going to maintain ratios. There's no real need to worry about the overlap or anything like that. But you definitely would not want. You could, these two fuse curves would work as part of the 0.1 seconds rule, because I am maintaining separation, but they don't maintain that 2-to-1 ratio that I would want, and they don't maintain that ratio that I would want to see, so there wouldn't be a need to do that from a fuse perspective, because just maintain the ratios, go away, leave me alone. All right, so, and remember, for example, that first example of the 1500 amps or the 2000 amps with the BAB downstream of an F-150, those would meet the 0.1 second rule. So the bottom line on 0.1 seconds is selective coordination systems will be coordinated as per the requirements of the NEC for 0.1 seconds. So if you selectively coordinated, you've exceeded the code requirements with regard to Article 517. If you are meeting the 0.1 second rule, which means the process that I just described, you're only coordinating in the overload region, then you're ignoring fault currents that would definitely not meet a selectively coordinated system. And then systems that achieve selective coordination exceed the performance of a coordinated system. Now, let me just one other mention here. I've heard people say, well, I coordinate to 0.01 seconds. And again, that's like chalk, that's like nails on a chalkboard, because, you know, if I say 0.01 seconds, you could misunderstand that to say I have separation of curves down to 0.1 seconds. That would mean that this BAB20 downstream of an F-150 could meet a 0.01 second discussion, depending upon your frame of mind, because you're ignoring the fault current that's in the instantaneous region. So do me a favor, if you're talking about selective coordination, talk about it with regard to the fault current that's passing through these devices. Give up on the discussion points of 0.1 versus 0.01 and all of that good stuff. Now, in the 14 cycle, Article 517 had 0.1 second coordination, but in other, emergency systems other than healthcare were selectively coordinated. In the 11 cycle, what 517 did was point to Article 700. So they had a selective coordination requirement if you were on the 11 or earlier, but they sort of separated themselves from Article 700 in the 14 code version. So if you're beyond 14 code, then you're doing 0.1 seconds. You're permitted to do 0.1 seconds. You're always permitted to go above and beyond bare minimum code requirements. Again, always consider you got to do a short circuit study, your equipment evaluations, all that good stuff. So my message to people is be clear in your specifications from a design perspective. You would not believe some of the stuff that I've seen in specifications that are very confusing. As manufacturers, we want that job. I don't want my competitor to get that order. So I am going to do whatever I'm going to look at the words that are in your specification. And if I can interpret that you want to do 0.1 seconds, I'm doing 0.1 seconds, because I'm not going to have to increase the size of overcurrent devices. Okay. If you say series, I've seen specifications that say I need a selectively coordinated system and everything needs to be series rated. They don't go together. Okay. And be mindful of that. You're not going to be so here's some examples of specifications that I've seen. Selective coordination. Graphically illustrate the adequate time separation exists. There's no mention of here on what the fault currents are. This is not as clear as it could be. Here's another one. Emergency systems, 0.01 seconds. I explained. In the mind of this engineer, he probably is considering fault current. But when you write 0.01 seconds, I'm going to make that BAB20 work downstream of an F-150 because I have separation of curves all the way down to 0.01 seconds, and I'm going to ignore fault current. And I'm going to make that on my order. My competitor is probably going to do that too. You're going to get quotes that all align with each other because they're doing the same mistake. Okay? So be clear in what you're asking for so that we all quote jobs the same. Right? Here's another example. Overcurrent protective devices in the electrical distribution system shall be selectively coordinated to 0.1 seconds. Selective coordination shall not be required. Selective coordination is all currents, all times per the code. When you use the term selective coordination and 0.1 seconds in the same word, what am I going to do? I'm going to do 0.1, but if you in your mind are thinking selective, I'm not going to get I'm not going to deliver what you need. So my suggested, I have some suggested language I'll put in a link down below that basically just be transparent and clear on what you want. Tell me what you want to selectively coordinate and what you don't want to selectively coordinate, because that's going to help the manufacturer, whoever's quoting that job, quote it accurately. And you don't want to change order after the fact, because if you've already installed stuff, this could be a very difficult problem to fix. I'm going to include this language down below. I'm not going to read you a sample specification. That wasn't my intent, but I do have an updated version of this for the different code versions of the National Electrical Code. So that's a 0.1 second overview. It's very easy to get that done. But what I want to do now is I want to move into how do we get selective coordination done? What's the process? I'm going to walk through this very quickly. So The first thing you have to do is secure an accurate single line diagram. The next thing you have to do is calculate fault currents. If you're not doing a 2-to-1 ratio with fuses, you're going to need that short circuit current value at each of the buses. Now, when you're in the design phase, you don't have the transformers. You don't know what these transformer impedance is. You have to make guesses. What you'll do is go to the manufacturer that you're going to be. You have to do a basis of design. You're going to base your design on a specific manufacturer that makes your life easier, and you're going to pick what the lowest. It's a 1,000 kVA transformer. You're going to ask that manufacturer what's the lowest impedance for those transformers and put that in as a ballpark figure. These conductor lengths, you're going to estimate those at pretty short. You can, if you know that you're going to have a panel that's on one side of a complex as opposed to the source being on the other side of the complex, you don't have to use 20 feet or 15 feet. You can use 100 feet as long as you know it's not going to get shorter than that, because when you're using breakers, if the fault current goes up, you're in a world of hurt, and you didn't plan for it. So assume a smaller, shorter, reasonable length on all of these. Your ability to estimate these lengths more accurately than your competition will give you a better quote on your jobs. So you're going to want to make sure you navigate around these lengths of these conductors. What else are you going to do? You're going to make sure that then you're going to pick these overcurrent devices, and then you're going to, in the design phase, you're going to start at the lowest device. So you're going to go to that lowest device and make sure that it protects the load or meets the requirements of the NEC. So if it's a light bulb, there's not much you have to do. But if it's a motor, you're going to have to plot the motor start curve and make sure that your breaker, that you have ample separation in that region. This knee is what changes a lot. That's where you go from locked rotor amps to full load amps, and this could change based upon what you're driving. If it's a rock crusher, this knee could extend up higher. If it's a fan, which with no resistance on startup, this knee can curve over much lower. You're going to need to plot this downstream of your next overcurrent device, and once that works, then you're going to work your way up through the system to the service equipment. This would be an example of a lack of coordination. So I've got a fuse curve. I've got a fast-acting fuse on a motor circuit, and on startup, that inrush current is going to open that fuse. I want to avoid that. I want clear separation in those regions to make sure that I can start my motor or I can energize my transformer. So the first thing you're going to do is you're going to grab the largest device downstream, device A, and you're going to compare that with the upstream device, and you're going to make sure you're coordinated. And you're going to do this all the ways up through the system until you get to the service entrance equipment. And you're just going to pick those devices based upon the logic methods that we just used. What did we do? We calculated the fault current. We plotted it on the time current characteristic curve. We plotted it on the time current characteristic curve. If the fault currents were in this region to the right of the instantaneous pickup, I went to the tables and used the tables. If I was using fuses, maintain the ratios from the manufacturer. If my fault currents are in this region down in here, I know I can use the selective coordination time current characteristic curves to determine my coordination. But I'm going to do an evaluation, and I'm going to work my way in pairs all the ways up to the main. I'm going to continue to do that. Now, if I, for example, I have to change a device upstream, I might have to go back down to the bottom and work my way up to make sure that any changes upstream is taken into consideration throughout the system. The process is a process of comparing curves to understand their performance based upon the current expected, maximum current expected to flow through them. So if I look at this set of curves here, I have 10 amps flowing through downstream of this 20 amp breaker. I'm not going to trip. If I have 100 amps flowing, I know that my downstream, my device A, that 20 amp breaker is going to trip somewhere between 1.8 seconds and about 6 seconds. So the downstream breaker is going to, but the upstream breaker, which is a 100 amp breaker, I believe, that's might be a little bit higher than that, but that breaker is not going to trip on that's a 150 amp breaker on that breaker. Now, if my fault current increases to 1,000 amps, now I know my circuit breaker downstream is going to trip instantaneously without an intentional delay. Okay, but so that's going to go instantaneously, but my upstream breaker is going to take anywhere from what is that? About 3 seconds to 10.8 seconds to trip. So I know I am selectively coordinated at 1,000 amps. If my fault current goes higher than the instantaneous pickup of both of those devices, I'm going to have to use something to figure out what's going on. So when I'm into the instantaneous region of both of those, so this is the evaluation that you're doing for each of the pairs as you work up through the system. And those two breakers happen to selectively coordinate at 1,500 amps. So I know that that would work. Now, another thing you have to consider is what breakers have to coordinate. You know, when I have a transfer switch in the picture and I'm looking at Article 700, 701, 708, which breakers have to coordinate with which? Because if this is an Article 7, this is your Article 700 system. This is outside of the Article 700 system. But what has to coordinate with each other? The 2020 version of the code clarified this for everybody, but it's been a debate for ages. The way this operates is the furthest downstream device has to coordinate with all upstream overcurrent devices per the National Electrical Code. D coordinates with everything upstream, including those breakers on the normal side, because the onus is on these breakers on the emergency side to coordinate with those. The requirement is not placed upon A and B. If I have to change A and B to meet the requirements on D or C, then so be it. But the requirement is on D and C devices because they're on the emergency side. They have to selectively coordinate with all upstream devices. That's sort of the way. This was a new informational note that was added in the 2020 cycle, and it's something that this is an area that you always have to worry about. And the fault currents that you're going to coordinate are not the fault currents from the generator. The fault currents are going to be the greater of whichever one produces more. I made a mistake one time in a presentation, said your utility is always going to give you the most fault current. But I had somebody tell me, no, I work on a hospital and the generators give me more fault current. So whichever one gives you the more fault current, that is what you're selectively coordinating to downstream. You don't have to selectively coordinate A and B per the National Electrical Code because they are outside of the range of the requirements of 700, 701, and 708. Those do not have to selectively coordinate. And I already talked about the tables. We're at 159, so I'm going to now take a look at the chat sessions here and see what we got, because we're at 159. We're right here at 2 o'clock. I know everybody's also has lives and work to do. We have the increased cables, so I haven't seen anything new on chat. Let me look at the. Dan Neeser says his 2 to 1 ratio. 2 to 1 ratio is not for all fuses. It's you have to go by the ratio tables that are in the published manufacturer's information. So can you provide a resume of the key points to do a coordination study for PDS and which software recommended? I don't like to recommend software. EDSA, easy, whatever. I look at software. I grew up on SKM. I remember Lon Lindell and the crew back in the early 90s when I was doing selective coordination studies. I'm familiar with that. So it's like, do you like Microsoft or Apple? It's whatever you grew up on is sort of where you'll be at. And find one that is economically priced for you and you can understand and has good technical support. And I don't see anything else on the YouTube side of the stream. So what I'm going to do now, for everybody's sake, it is 2 o'clock. I'm going to close my little chat window and I am going to open up the Mentimeter code